In this video, we are going to solve another Euler Buckling problem. And so this problem statement asks us to find the minimum cross-sectional area of the square column shown such that the column yields and buckles at the same time. So we're given what the elastic modulus is and also the stress at the yield point of our member. So first thing we want to do is just write down our equation for Euler buckling. Since we're looking at a buckling problem, we're going to be reusing the buckling equation, which is going to be P critical is going to be equal to pi squared times E times I over L effective squared. So first thing we want to do is we already have our E value, which is our elastic modulus, so we're going to want to find our moment of inertia I and also our effective length. So the first thing we do, we're going to find our moment of inertia. So if we look at this cross section right here, and then if we put our axes on it, this should be a value of, let's see, this is going to be z and this is y. So if we look at that, since it's a square, both the moment of inertia about I and IZZ are going to be equal to each other because they have the same base and height. We're both, in this case, we'll call this distance A, which is the same on all sides. So if we use that variable A and solve for what IYY is, which is going to be equal to IZZ, that's just going to be equal to 1/12 BH cubed, and then when you plug in A, it ends up just being 1/12 A to the fourth. So another thing that we want to know, since we're looking to find the cross-sectional area of our column rather than just what one dimension is, we can say that the area of our column is going to be equal to A squared. So that means you can rewrite IYY, which is the same thing as IZZ. You can rewrite that equation as 1/12 big A squared, which is the area squared. So that's going to be that equation. So that's what we're going to solve for in the end. And so next thing is to just find our effective length. So if you remember from your 207 class, the effective length for a cantilever like this isn't just the length of the length of your segment. It's actually going to be the length times 2. So our effective length for this problem is going to be 2 times L. So it's going to be a value of 20 feet, which is equal to 240 inches. And so if you don't remember where that's from, just go back and look at your lecture notes. But yeah, so since this is a cantilevered kind of column, it has a free end on top and a fixed end on the bottom. That means it's going to deflect more than if it was pinned at both sides per se. So that's why you have to have a larger effective length. So now the last thing that we have to do is just relate our yield stress to our critical point. So if we write that down, so we just need to relate sigma y, which we're going to call sigma of the yielding, to our force, our axial force, P crit. So in order to do that, let's remember what yielding actually means in this case. So when we say that this column is going to yield, since there's only an axial force acting, the stress in this system is just going to be a force over an area. So we're going to say, okay, so that means our yielding stress, our yielding stress is just going to be equal to this P critical over the area of our section. So this is just axial stress that we're getting. So we're saying that since we know the problem statement gives that the force it takes to yield the structure is going to be the same as the force it takes to buckle the structure. So that's why we can just say that P critical is going to be equal. P critical is just going to be equal to the yield stress times the cross-sectional area. So now we just plug this into our Euler Buckling equation. So when you plug everything in, you should get that the yield stress times the cross-sectional area is going to be equal to pi squared E times I over L effective squared. So now we can just plug in all the values that we know. So this is going to get us a value of 1.2 KSI times A, which is equal to pi squared times 2,400 KSI This is going to be times our I value, which we found to be 1/12 a squared. And this is all going to be over 240 inches squared. So when you plug all that in and then you go ahead and solve for a, you should get a cross-sectional area that is going to be equal to 35 inches squared. And that will be our final answer.